It's an alien landscape where magnetic tornadoes twist upward tens of thousands of miles. Mysterious dark spots, large enough to engulf the Earth, ebb and flow. And violent eruptions shoot tons of charged particles into space at speeds of over 2 million miles per hour. This is not some strange world on the other side of the galaxy. This is our sun. And now, new technologies are allowing us to see it like never before. Satellites are giving investigators new insights into centuries-old mysteries.
Whoa, did you see that?
Boom, there goes a flare.
That is really a quantum leap in solar physics, a continuous eye on the sun.
How does our sun work? Where does its power come from? And how can its inner workings impact us some 93 million miles away? Finding answers has a new urgency.
Before the expert by about 6 to 8 hours.
And the bigger hit.
The bigger hit.
Our sun has a dark side. It's violent storms capable of taking down the electrical grids that power our daily lives.
Repair could take weeks, months, and even in a worst-case scenario, up to 10 years for a full recovery.
If you can imagine a world without electricity, you're really going back in time.
Now, join scientists on a quest to understand the secrets of the sun. Dive deep into its core and ride out its spectacular storms. Dawn, February 15th, 2011, Boulder, Colorado. The team at the National Space Weather Prediction Center begins its day as it usually does, carefully watching the surface of the sun.
Okay, a 10 centimeter came in today.
Although 93 million miles away, forces here can impact Earth in surprising and destructive ways.
For the smaller,
The M6.
for the M6, you see this. The very first one is the M6.
Today, after years of relative calm, a satellite detects something. A dramatic explosion on the sun's surface. A violent solar storm that would dwarf Earth is erupting, releasing a massive shockwave, hurtling towards us at over 1 million miles an hour. Right now, no one is sure what to expect.
But I think that the M6 is going to get here.
We have to determine when that thing is going to impact Earth's magnetic field.
8 hours.
It's going to be sometime tomorrow, perhaps later in the morning, later at night. That's exactly what we're trying to determine. In fact, I have to join the discussions right now, so I'll get back with you.
The team models the approaching storm.
So 15Z for the arrival of the CME. This is it here.
Right
okay.
there.
Their simulation shows it racing out from the sun on the left towards the small dot on the right,
So we're looking at about
Earth. The solar storm carries a 1-2 punch. First is a solar flare, releasing an outburst of X-rays that can reach Earth within minutes. The second, more ominous threat arrives a few days later, a phenomenon called a coronal mass ejection, or CME. It's a wave of billions of tons of electrically charged particles, seen here in this repeating image as it ripples away from the eye of the storm. Together, they could hit like a cosmic tsunami. Delivering a surge of radiation and an electrical spike of trillions of watts, potentially crashing the power grid. Sound far-fetched? In March 1989, in Quebec, Canada, that's exactly what happens. One by one, power stations crash, disabled by the overwhelming power surge caused by a CME wave. In less than 2 minutes, 6 million people are left without power. Recently, NASA's Jim Green finds evidence that an even bigger solar storm hit Earth in 1859.
And what we found was the granddaddy of geomagnetic storms, and that was just 150 years ago.
If we had a geomagnetic storm of that intensity today, the National Academy suggested that the impact on critical infrastructure could be catastrophic. And the big concern is the electric power grid.
The massive electrical surge from a CME wave could overload power lines and melt transformers, blacking out entire cities.
Repair could take weeks, months, and even in a worst-case scenario, the National Academy suggested up to 10 years for a full recovery.
If that occurred, if you can imagine a world without electricity, you're really going back in time.
It's not just the power grid that's at risk.
More and more, we rely on technology that could be affected by the sun. Global positioning satellites, long-distance communications, airplane tracking, astronauts in space.
Roger, how does it look?
So there's an urgency in understanding what it is that the sun is doing, what's it going to do next, and how can we prepare for that and respond to it.
Worried or not worried?
Well, I would be just a little bit worried,
Concerned.
concern right now. We'll be watching and monitoring it very closely here in the coming days.
We've gazed at the sun since antiquity. We've worshipped it and built entire cultures around its power. We marvel when it's eclipsed during the day, and when its power lights up the night sky with dancing curtains of light, the aurora. Its power and size are awesome. It is so huge, 1 million Earths could fit inside it. Temperatures at its core soar to 27 million degrees Fahrenheit. It's been shining for over 4 billion years, and will do so for at least 4 billion more. Yet for something that has such an overwhelming influence on our lives, the sun is mysterious. How does the energy generated in its core reach us as sunlight? What processes are at work inside the sun? How do these powerful inner workings generate explosive solar storms? These are some of the mysteries scientists must understand to protect us from the sun's darker side.
The sun can really surprise us.
The sun is elusive,
Crazy,
Complicated.
crazy,
Incredibly dynamic.
crazy.
With explosive potential.
The key to that explosive behavior lies deep beneath the sun's blinding surface. Until recently, seeing inside the sun was impossible. Understanding its internal processes, a pipe dream. But an accidental discovery changes everything.
Until the 1960s, much of solar physics relied on things that were like solar dermatology. It was things that were right at the surface or just skin deep.
But as physicists study the sun in more detail, they make a surprising discovery. The surface seems to be vibrating, like ripples on a pond. Initially, they think the vibrations are the result of defective instruments.
They couldn't get rid of them. They built better instruments, the ripples were still there. They looked at it for 10 years. And they did conferences, they all talked about it, and they harumphed. But what it turned out to be was just sound waves.
It is an astonishing revelation. No one expects that the sun can generate sound waves. It leads scientists to see the sun in a completely new way. Our sun vibrates like a giant pipe organ. But instead of air producing the notes, churning gases deep inside send sound waves rippling through its interior.
Because a sound wave changes as it moves through different material, we can look at the different frequencies and determine what's happening inside the sun.
Geologists are familiar with this. By studying sound waves passing through the Earth's crust, they can see the layers below our feet. A technique called seismology. Similarly, sound waves moving through the sun's interior reveal how it's made up.
I can use this organ to illustrate how sound waves work inside the sun. For example, if I hit this low note, it comes from one of these big pipes, big deep sound. And on the sun, that corresponds to a wave that goes very deep into the sun and brings back the information from deep down in the sun. If I turn to a high note, it comes from a much shorter pipe, and on the sun, that's telling us information about very close to the surface of the sun, not very deep at all into the sun.
There are 10 million different frequencies resonating in the sun. Deciphering them leads to a seismic shift in understanding its structure, creating a new science, helioseismology.
Once the helioseismology came along, we could not only see what the surface was, but we could actually tell what the physical processes were underneath. So by looking inside, we can actually see what the sun is doing.
It is a powerful tool to see beneath the sun's surface. Studying the sun's sound waves reveals a complex, multi-layered machine. Directly beneath its blazing surface is a zone of perpetual churning. Next is a layer where light takes thousands of years to cross. At the center is the sun's core. It's the smallest region, but it's over 25 times the diameter of Earth. This is the powerhouse of our star. Everything we experience on Earth, sunlight, heat, and the effects of solar storms, starts here. So what's it like here? What's the core made of?
Well, the sun's a crazy place, right? It's far too hot to be a solid. We know that. Right? Heat it up, it's far too hot to be a liquid. And so you think, well, it's a gas, right? Well, not really. It is this gaseous soup of charged particles that we call plasma.
You're more familiar with this soup than you might think.
There are plenty of examples. Fluorescent light bulbs, flames, neon lights, perhaps fancy TVs that I can't afford, but these are all plasma. Plasma is sort of all around you.
But plasma is radically hotter at the sun's core. The closest thing on Earth is lightning. During thunderstorms, electric charges build up, creating lightning bolts that reach tens of thousands of degrees.
That's pretty hot, but it's nowhere near as hot as in the core of the sun. So if you're to travel into the core of the sun, the plasma would be 15 million degrees.
As the sun formed, hydrogen gas at its heart was crushed under the weight of the material above. Eventually, temperature and pressure rose so high, the hydrogen atoms broke apart into electrons and protons, creating plasma.
And it's under these extreme conditions that something really, really cool happens. Nuclear fusion.
It's the same atomic process inside the hydrogen bomb. Under tremendous pressure, protons in the plasma fuse together, releasing photons, minuscule packets of heat and light. An unimaginable number of photons are made every second, generating the sun's incredible power, some of which reaches us as sunlight. This atomic alchemy converts over 4 million tons of mass into energy every second in an endless loop.
That much mass into energy is the equivalent of 10 billion hydrogen bombs being created every second. The sun does this day in, day out. It's been doing it for 4 billion years, and it's going to continue to do so long after I'm gone.
The energy of billions of bombs is released in the core every second. This begs a simple question.
So you could ask, well, why doesn't the sun blow itself apart? It's because there's this beautiful balancing act that occurs. In the core of the sun, you've got this pressure from all of this fusion pushing outwards. And the sun is huge, so you have all this gravitational pressure pushing downwards. And so you've got gravity pushing down, and the sun trying to blow itself apart from the inside, and it is this beautiful balancing act between the two that keeps the sun in one piece.
This light, born at the core, reaches us after a remarkable journey. Away from the core, pressure and temperatures drop, and nuclear fusion stops. Now, each photon begins a tedious journey through the sun's thickest layer of plasma, a region called the radiative zone. Although squeezed less than at the sun's center, the plasma is still very dense, and photons struggle to move through it. Each packet of energy is continuously absorbed, then spit out by the plasma particles.
In that particular part, there's no energy being generated, but the energy is transmitted by the radiation. So that's why we call it the radiative zone, not too surprisingly.
The photons slowly bounce through the plasma here, ricocheting in a zigzag path called the random walk.
So imagine that you're in a crowded room and you're trying to make your way through and you greet other people. And each person you greet, you have to say hello to, and then you move off in another direction. So it takes you a long time to get from one place in the room to another because you're just kind of meandering your way around the room. So the same way the photons in the inside of the sun, they don't have a preferred direction. All they want to do is they want to be moving and they want to be greeting other particles.
Though moving at the speed of light, 186,000 miles a second, it takes photons over 100,000 years to cross the zone. Eventually, the photons reach a boundary where pressures drop again. The plasma thins, and moving through it gets easier. The photons still pack a lot of energy. Now, they leak out into the convection zone, heating it from below. The thinner plasma in this zone makes the photons move in a different way.
So instead of bouncing, all of a sudden there's an ordered motion. So it's as if all of a sudden someone said, lunch, and all the particles decided, oh, we all have to go this direction. You still have to wait in line to get out, so it takes a month to get from the bottom of the convection zone to the surface, but it's a relatively short period.
During this short period, heat from the photons sends plasma here into perpetual motion, a maelstrom of churning 125,000 miles thick. Think of it like a massive lava lamp.
There's heat that enters at the bottom from the light bulb. It heats the material, and the blob rises to the surface. When it gets to the top, it cools off. And when it cools, it gets more dense and falls back down. This is a good analogy for what's happening inside the sun. We have the core of the sun heating the material at the bottom of the convection zone. The material expands, and it carries the energy upward until it gets to the surface.
These incredible images reveal convection at the sun's surface, rising and sinking plasma that creates a mesmerizing structure called granulation.
The granulation cells are about the size of the state of Texas. They only last for about 12 minutes, so there's an incredible amount of energy. It's a very dynamic, very chaotic place. And all of the activity is going on the surface of the sun where we can see it.
Photons produced at the core finally reach the surface. They emerge as a weakened form of solar energy. This weakened energy reaches Earth in 8 minutes. We know it as sunlight.
So 100,000 years, about a month, and then 8 minutes. Once you get to the surface of the sun, it just takes 8 minutes to get to where you can see it.
Unimpeded, the trip from the core to the surface would take the photons a matter of seconds. In reality, the sunlight that shines on us today may have been created during the last ice age. Energy reaching the sun's surface doesn't just result in sunlight. It can also trigger solar storms. Understanding the sun's destructive power requires 24-hour precision surveillance, something that, until recently, was impossible to achieve.
5, 4, go for main engine start. 3, 2, 1, 0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory.
February 2010. NASA launches its most sophisticated solar satellite yet. The Solar Dynamics Observatory, or SDO for short.
Coming up on Mach 1.
SDO is the first satellite to deliver almost continuous, super high resolution coverage of our nearest star, giving researchers unprecedented access to the sun and its secrets.
The first day was very exciting. We knew we were going to open our doors to actually let the sunlight into the instrument for the first time.
We started looking at the first pictures, and it was almost in focus. And as soon as we focused it, it was just beautiful.
The new images reveal the sun like never before. An alien landscape where strange structures ebb and flow. Giant tornadoes, hundreds of thousands of miles high, that could easily engulf the Earth. And superheated bubbles of plasma the size of Alaska.
When I look at the pictures, I think they're really beautiful. I'm struck by the dynamics of it. Things are changing all the time, no matter where you look. And I'm also pretty daunted by the complexity of it all.
That's not surprising. Previous satellites only revealed a portion of the sun in high resolution. Now they see it in mind-boggling detail.
Now, in order to look at the Solar Dynamics Observatory images that we're bringing in every day, we've built this very special wall, which is 9 high-definition television screens together that can display these images, so that the instrument and the display system together are an entirely new way of looking at the sun.
We can see all the details of what is going on, and that is really a quantum leap in solar physics. Being able to see all of that all the time, a continuous eye on the sun.
One of the most important aspects of SDO is its ability to see sunlight across a range of wavelengths, the equivalent of looking at things glowing at different temperatures. Our eyes are most sensitive to sunlight glowing at around 10,000 degrees Fahrenheit. At this temperature, the sun's surface looks almost featureless. But at hotter wavelengths, normally invisible, a far more dynamic picture emerges. The February 15th, 2011 storm is a perfect example. In this repeating image, at around 90,000 degrees Fahrenheit, SDO captures just a ghostly trace of the CME wave. But at just over 1,000,000 degrees, the superhot plasma rippling away from the eye of the storm is much clearer. This allows researchers to see coronal mass ejection waves evolving across the entire sun.
This is an absolutely amazing time for solar physics because of these beautiful high-resolution images that allow us to understand better the physics behind what's going on when solar storms erupt.
There's that one last photo. Look at this one here.
Back at the National Space Weather Prediction Center,
That's the M1 here.
Bill Murtaugh tracks the storm's CME wave. It carries 1 billion tons of plasma and is now only about 20 hours from Earth.
We're bringing it in mid to late on the 17th into the 18th.
What they see is alarming.
Well, there's actually 3 CMEs that we're looking at. So we bumped up some numbers for late tomorrow. Yeah.
It's not a single CME wave, but 1, 2, 3 of them.
We won't call it the perfect storm yet or anything, but conditions are lining up for some significant space weather.
Their models show trajectory and speed, but the big unknown for Murtaugh is how powerful the waves will be when they hit. The answer lies in a force that governs the sun: magnetism. We're all familiar with magnets. They produce an invisible force that pushes and pulls on charged particles. In fact, Earth has a magnetic field that protects us against threats from the sun. But we are less familiar with the sun's magnetic power, which researchers believe plays a major role in driving solar storms.
We've essentially learned that it takes 2 things to make a star magnetic. It needs to have these convective motions right underneath the surface, the bubbling of the gas. It needs to spin, and the faster it spins, the more active it becomes. And wherever those 2 things, the bubbling and the spinning, can interact, that's where we see the strongest magnetic activity in stars.
Astronomers know that the surface of the sun spins in a strange way. Travel from the poles of the sun towards its equator, and you'd notice it turns faster. Analyzing sound waves inside the sun reveals that the plasma layers beneath the surface also spin at different speeds. That's because they act like fluid, which gets denser towards the core. The interior of the sun is a place of spectacular turmoil. Turmoil that's the key to the sun's magnetism.
The motions there, the convection, the differential rotation, the motion from equator to pole, are driving a new force. They're driving a magnetic field. There's a dynamo at work here. a dynamo that's generating a force that we actually experience here on the Earth.
It works like a giant wind turbine. Churning plasma in the convection zone stirs up powerful electrical currents, which generate a huge magnetic field.
Have upflows here and downflows coming down this way, right?
The holy grail for scientists is understanding exactly how this dynamo generates solar storms. The clue lies deep within the convection zone. Magnetic field lines normally run from pole to pole. But with all the turmoil in the convection zone, that pattern can't last. Rotating layers stretch them horizontally. Convection twists and braids them. Under immense strain, they begin to kink upwards towards the surface.
Imagine this spring is a magnetic field line. The magnetic field inside the sun is amplified, is strengthened by the rotating motions and the shearing motions and the churning motions inside the sun. It wants to expand upwards, and it does, until it pokes out through the surface of the sun.
Tracking invisible field lines is normally impossible. But plasma plays a critical role.
Even though the magnetic field lines themselves are invisible, the plasma, which is heated and hot, can light up along these paths. In maybe the same way, you could think of a highway, and at night you wouldn't see the highway at all, but with the cars with their headlights on, you'd see the path of the highway.
Watching field lines is critical to understanding solar storms. As field lines emerge, they form loops. One end has a positive pole and the other a negative pole. Churning plasma beneath the surface twists these loops, pumping them with energy. If twisted enough, positive and negative parts of the loops cross. When they do, they short circuit with a tremendous explosion. The energy released heats the plasma to millions of degrees, resulting in a spectacular solar flare. It's the final dramatic stage of a very long journey. Photons formed in the core make their way to the surface. Some pass directly into space as sunlight. But in the process, that surging energy disturbs the convection zone, generating a magnetic field. The field lines wind up to the point that it explodes in a solar flare. Now, SDO provides a complete and unprecedented picture as these events evolve.
This is beautiful because the hot gas outlines the magnetic field lines that we would otherwise not be able to see. And here you can see even a twisting structure as some of the mass drains back down to the surface, and a lot of it escapes in the eruption. This is the essence of space weather, or solar storms.
This explains how flares form, but it's not the end of the story. Crossing magnetic field lines can cause nets of plasma to be flung into space. This is a coronal mass ejection, a CME wave. The portrait of how solar flares and CME waves form is coming into focus. But a key question remains. CME waves can travel 93 million miles to Earth in a matter of hours. So what gives them such explosive energy? Part of the answer is hidden here in the sun's atmosphere, the corona. It's made of superhot plasma that blisters at over 3 million degrees Fahrenheit. 300 times hotter than the sun's surface. Some scientists suspect that this heat powers massive gusts of energy that blast CME waves toward Earth at incredible speeds. But why the corona is so hot is an enduring mystery.
Understanding it's essential if we want to get to the bottom of how the sun drives space weather and the impact of the sun on the Earth.
The fact that the corona is so much hotter than the surface flies in the face of physics.
The sun's corona is a very odd place. Take this fire, for example. As I put my hands close, sure, it's warm, but as I pull them away, it gets cold. That's not the case on the sun at all. As you go in close, it's definitely warm, but as I pull away, it actually gets warmer still.
Recently, Japanese investigators observe high-velocity jets of plasma shooting up from the near surface. McIntosh suspects these jets deliver heat to the corona, but he doesn't have a way to confirm it visually until he turns to SDO for help.
Lo and behold, we actually managed to join the dots and see, yeah, these objects that we could see moving out of the lower atmosphere at high speeds, kind of like these licks of flame, really were reaching a couple of million degrees. It was really a tumultuous moment. We kind of looked at each other and said, wow, what have we just done?
They've shown that the plasma jets accelerating upwards from near the sun's surface generate tremendous heat. As a result, temperatures in the corona soar to 3.5 million degrees. If confirmed, it represents a huge leap forward in understanding CME behavior. The immense heat of the corona acts like a wind in a raging gale. It's constantly pushing on the plasma draped on the field lines, billowing them out like sails pulling on a mast. Like solar flares, when magnetic lines cross, there can be an immense explosion. In this case, the lines are cut and the sail whips off into space. Loaded with 1 billion tons of highly charged plasma, the CME wave can wreak havoc on electricity-dependent Earth. At the National Center for Atmospheric Research, this violent event is captured by satellites.
Now, to see the CME, we need to create a little artificial eclipse. To do that, we block out the light from the disk of the sun, and that's this little circle here. But what that allows us to do is to see this extremely faint, high-speed thing shooting away from the sun. This one moves at about 1,000 kilometers per second.
By enhancing the picture and slowing it down, it's possible to see the shockwave moving at over 2 million miles per hour. Though we have a better understanding of what causes solar storms and how they reach us, there is still a final pressing problem.
Trying to predict when solar storms are going to occur on the sun really requires a lot of detective work. Basically, we're looking for clues and observations to tell us when potential storms might occur.
The best clue comes from these. Sunspots. Dark patches which can linger on the sun's surface for weeks at a time.
A sunspot is a massive region, several times the size of the Earth, which appears on the sun as a dark spot. It's dark because it's relatively cool compared to its surroundings. And it's cool because the magnetic fields are so strong that they're suppressing the flow of heat from below.
The strong magnetic fields which create sunspots are the breeding ground for solar storms. The challenge is trying to decipher a pattern for when and how many will appear.
As we watch sunspots over a period of many years, we see something very interesting. The number of sunspots at any given time will wax and wane over a period of about 11 years. And since we now know that sunspots are associated with strong magnetic fields, this tells us that the sun's magnetic fields are likewise going through a cycle.
The constant churning and twisting inside the sun creates a powerful dynamo, the biggest electrical generator in the solar system. The magnetic field lines it produces get so wound up that roughly every 11 years, the magnetic poles of the sun reverse. After that, calmer magnetic activity prevails and fewer sunspots form, a period called solar minimum. But because of the sun's turbulent nature, the field gradually winds up again. As it does, magnetic outbursts are far more common, a period called solar maximum.
The solar cycle actually determines the personality of the sun. During solar maximum, it can get very angry and it can throw off solar storms that are sometimes directed at the Earth. And during solar minimum, it becomes much more subdued. There aren't as many sunspots, there aren't as many solar storms occurring. The activity cycle basically determines how the sun is going to act.
Prior to the solar storm of February 15, 2011, things were pretty quiet on the sun. But that outburst marks an ominous turning point. The sun's magnetic activity is winding up again as it heads towards solar max. Just a few days ago, Bill Murtaugh and the team at the Space Weather Prediction Center witnessed the turn.
Arrival of the X2 and the M6, if it comes in with any geoeffectiveness, between 12 and 1800.
So that's what we're seeing.
It's now time to let the world know what it might expect.
Nothing higher than
In the next couple of minutes here, we're going to have to make a decision and make the prediction that this coronal mass ejection is going to arrive at whatever time tomorrow, and the geomagnetic storm will ensue, of course, once it arrives.
With the event we had...
Murtaugh knows that the severity of the storm depends mainly on two things: how strong the CME's magnetic field is, and at what angle it hits Earth's own magnetic field. CME waves approach Earth like a slowly rotating shield. One end is positively charged, the other negative. With magnetism, opposites attract, and like poles repel. If the wave's positive pole lines up with the Earth's positive pole, most of the power of the storm will be repulsed. But if opposite poles line up, the plasma the waves are carrying will hit with full force.
Did you say it came in at 115?
114.
Murtaugh makes his final assessment only hours before impact.
It could be larger, more complicated, typically, than just your single coronal mass ejection.
I think we've nailed the forecast.
Okay. I'd like to think so.
According to the observations, the CME wave will be repelled.
We don't expect it to be too strong. We'll see moderate storming levels, which is good enough to produce some aurora borealis down in the United States, down along the Canadian border, northern tier states, and it will cause some minor problems to the power grid and whatnot.
Space weather for the next 24 hours is expected to be minor. Radio blackouts reaching the R1 level are expected.
This time, we dodged a bullet. But disturbing evidence suggests the Earth will not always be so lucky. It's a cautionary tale. NASA's Jim Green discovered it while researching a book on the American Civil War at the Library of Congress. Green found news accounts from 1859, which caught his eye.
I would run across articles about aurora. Fabulous aurora. And this really piqued my interest because it's in my field. It seemed as though the armies of heaven were engaged in terrific, though noiseless, conflict. This terrific aspect soon subsided into a more beautiful and brilliant appearance, a few of which I can only refer to.
The reports tell of auroras so bright, miners in Colorado wake up and go to work thinking it is dawn. Other accounts tell of a more harmful impact on the lone electrical system of the day, the telegraph.
One, for instance, because of the induced current on their system, overheated the battery and started a fire, nearly burnt down the telegraph office. Another operator was burnt so badly he ended up into the hospital.
Green uncovers numerous reports of auroras seen not only across the United States, but around the world. The evidence is clear. Earth was struck by a superstorm in 1859, the result of two massive CME waves.
Those two storms were not only enormous, but they happened one right after the other. No one alive has seen anything like it.
On the day before the waves hit, a British astronomer observes a giant sunspot group light up with two massive flares. The second CME wave hit 18 hours later, allowing Green to calculate its speed, 5 million miles an hour, plowing into Earth at almost 4 times the speed of the February 15, 2011 CME waves. Using the various reports, Green is able to reconstruct the 1859 storm. The accounts suggest that the poles of the CME waves were aligned, and instead of being repulsed, the waves hit with full power. The charged particles funnel down into the atmosphere, electrifying it like a giant neon sign, producing dazzling aurora displays. The storm is so intense, Earth's magnetic field all but collapses. Millions of tons of plasma spill towards the equator, and a powerful electric surge pulses over the globe. For the largely pre-electrified world, the moment passes with minimal damage. That might not be the case today.
It has the potential of knocking out power grids. And if it burns out transformers that are hard to replace, we may be without electricity in many areas for a very long period of time. There's only a few places that make these 125 kilovolt transformers. It takes several months to make them. And if you burn out half of them, we're going to be shooting squirrels and chopping wood out the backyard for a long period of time just to survive.
Everything grows,
building up.
but the 3D's really...
Today's solar scientists believe it's not if, but when the next big one will strike. With the next solar maximum due in 2013, it begs an all-important question. Can we predict when the next solar storm will hit?
No.
Maybe.
No.
Maybe.
No.
Maybe. And the reason why is we've learned so much about the sun. We're getting better at it, but we have a long way to go. And the more we look at some of these historic events, the more we get a deeper appreciation for what we need to know.
Today, we see the sun better than ever before. We're beginning to understand it from the inside out. But its unpredictable personality means there will always be uncertainty when living with a star.
And leaving in its wake the strangest phenomenon in the cosmos. A black hole.
Nothing survives encounters with black holes. The black hole wins. It wins every time.
When something falls into a black hole, it's essentially gone from our universe.
They rip stuff apart and eat them. And then they burp and they're ready for the next course.
And now, evidence of something even more ominous. A new kind of black hole. Of unfathomable size and power.
That's a big galaxy, and right down at the center, we think there's probably a black hole that's got a mass that approaches 1 billion suns.
Today, scientists are finding black holes are bigger, stronger, and more destructive than they ever imagined.
It creates energy fields that would fry any life in its vicinity.
Not only do they consume everything that comes near,
You stick your finger down in there, you ain't getting it back.
but their power may reach across galaxies and beyond.
Did the universe really have to be made with these things in it?
We'd like to think they're far, far away. But what if, in our own cosmic backyard, there lurks the monster of the Milky Way? Right now on Nova.
This is just enormous.
As he pores over a set of X-rays, Brian McNamara struggles to diagnose a complicated ailment.
The rings on this one. So that's pretty strange.
But his patient isn't a person, or any earthly creature. It's a cluster of galaxies, 2.5 billion light-years away, with a giant blast of energy spewing from the center. This is the most powerful explosion in the universe since the Big Bang.
To put this on sort of an Earth scale, it's equivalent to about 1 trillion atomic explosions. So it's an enormous amount of energy.
What could produce such awesome power? Whatever it is, it seems to live at the very core of galaxies. And many believe our own galaxy, the Milky Way, is not immune, harboring a powerful secret at its heart. What could lie at the center of the Milky Way? One of the pioneering explorers of our galaxy is Eric Becklin. He's been trying to unlock the mysteries of the galactic center for more than 40 years. But first, he had to find it.
Back then, people weren't even sure where the center was. There was some vague understanding. There was a radio source called Sagittarius A, a very strong radio source, but there was even debate whether that was really the center or not.
Examining other distant galaxies, astronomers knew that the center is usually the brightest spot, tightly packed with stars. But when they tried to pinpoint the center of our own galaxy, the Milky Way, they ran into a problem. The central stars were shrouded by cosmic dust.
There is so much dust between us and the galactic center, it is completely opaque. You do not see the stars in the galactic center. The most powerful telescopes cannot see it.
But there are other kinds of light that can pass through, like infrared, a form of light and heat invisible to the naked eye that travels in slightly longer waves.
Infrared radiation gets through the dust because its wavelengths are longer and the dust just kind of rides on the infrared wave.
In the 1960s, Becklin belonged to a Caltech team that bought an infrared detector from a military contractor and attached it to the end of a telescope.
It was in August of 1966. I was up at Mount Wilson. It was a beautiful night on a small 24-inch telescope. And as we were looking with the infrared detector, we were seeing more and more stars.
A simple chart recorded the infrared light of stars. Stars that until then had remained hidden behind a veil of dust and debris.
This is a signal in the infrared, and each star gives you more signal. And we were building up, as we were getting closer to the center, more and more stars. We were actually seeing through the dust for the first time, and then came to a peak, and then back down again. And I knew immediately that that was the center of our Milky Way, and that I was the first person to actually see the star in the core of our galaxy.
Located the heart of the Milky Way. From our perspective, an inconspicuous speck near the constellation Sagittarius. As a giant spiraling disk of hundreds of billions of stars, 100,000 light-years from end to end. Our sun, about halfway out from the center, sits in the peaceful suburbs. But at the galaxy's core, the neighborhood gets more exciting and dangerous.
There's a lot of gas. There's a lot of dust. This is absolutely the most crowded place in our galaxy.
From Earth, we can see a few thousand stars with the naked eye. If you went to the galactic center, there would be millions of stars filling the sky.
It's the big time. It's where the show really goes on in the galaxy. And so if you go there, you're very much aware of being a tiny little mouse in Times Square, and somebody's liable to step on you.
For years, scientists suspected that a powerful force dominated this galactic Times Square. It had to come from an unimaginably massive object. Some thought it had to be a black hole. An object so strange, it's hard to describe.
What's a black hole? It's a region of space.
It's a point of infinite density. We don't know how to wrap our brains around that. If you fall in, you never come out.
It's not the point of no return, it's the sphere of no return.
Now you throw in a hungry beast in the middle of it all.
It's this monstrous, mysterious thing.
And if you can imagine taking a bowling ball
that, I don't know, eats everything. That's not true.
You have something, you drop it off the top of a building, and you're falling into the deepest well you can possibly imagine. Physicists have just as hard a time as anybody else understanding this sort of thing.
It's a black hole. There's no other phrase we can possibly use to describe it.
The current idea of this bizarre creature comes from a radical view of space, time, and gravity. Welcome to the universe according to Albert Einstein.
Albert Einstein had this crazy idea that space and time were curved, and it was the curvature of space that gave the appearance of gravity.
We tend to think of space as rigid and stable, but Einstein proposed that space and time are woven together in a flexible fabric. Massive objects like the sun actually bend and warp the fabric of space-time, creating troughs that smaller objects can fall into.
What actually happens is matter warps space-time. So the very space, the three-dimensional space that we walk through, warps slightly. Warps in on me ever so slightly, but because we're not very massive, it's so minuscule that we don't sense it.
If an object is massive enough, like the Earth, it will warp space-time so we can sense it and fall towards it. That's gravity. But what happens if an object is much, much more massive than the Earth or the Sun? In theory, it could warp the fabric so much it would create an actual hole in space-time. Once something fell in, it couldn't escape, not even light itself.
So imagine a place where the gravity is so strong, turning on a flashlight. The light would go up and it would never leave. It would curve and come back down just the way a tossed ball on Earth is not traveling fast enough. It goes up, curves, and comes back down.
Space itself is falling inside the black hole. It's rather like a river falling over a waterfall. It's like that, except it's space itself that's falling over the cliff. There's a place where the space starts moving faster than light. So the light, which is trying to get out, it's rather like a kayaker trying to make their way upstream on a river that's going too fast. They get dragged down to the center of the black hole.
Gravity becomes a riptide. The closer you get, the stronger the current. Eventually, you reach the event horizon, the point of no return. Deep inside, whatever goes in is lost in a point of infinite density.
The matter goes inside the surface of the black hole, shrinks down to the very center, where it gets destroyed in a region of infinite warped space and time, and it's gone.
And so, it seems, are the laws of physics. At the center of a black hole, all equations break down. Even for physicists, what happens deep inside a black hole is a mystery.
We're in want of a new idea about how to explain what matter does at the center of a black hole. We're in need of a new law of physics.
Einstein himself concluded black holes were too strange to be real.
Albert never really liked the idea of black holes. He thought they were anathema. This was something that nature should avoid. The places where space and time became infinitely twisted up, he thought, no, nature shouldn't allow that.
Black holes are certainly odd beasts in the universe. They were thought to be peculiar, so peculiar as to perhaps not even really exist in the real world. Simply because your equations show that they can exist doesn't require that the real universe has them.
But over the years, suspicions rose. Stars were found behaving strangely, orbiting invisible objects, moving faster than expected.
Even though a black hole emits no light, is completely invisible, we know exactly what effect a black hole is going to have on its environment, on the stars in its vicinity, on the gas that wanders a little too close. So, will we ever see a black hole? No. But that's not what's important here. What's important here is we can see its paw print.
Suspicious that an enormous black hole was dominating the center of the Milky Way, Eric Becklin was eager to find its paw print. But even with infrared technology, when Becklin pointed the most powerful telescopes on Earth at his target, all he saw was this, just a blur.
The biggest obstacle that we had was the turbulence in our own Earth's atmosphere was blurring the images.
Even when the sky is clear, the gases in Earth's atmosphere are always on the move, distorting distant objects. To bring his view of the galactic center into focus, Becklin would need help. So he appealed to Andrea Ghez, an expert in dealing with the atmospheric blur.
The problems of the Earth's atmosphere is very much like the problem of looking for a penny at the bottom of a river that's moving, where the water is moving by very quickly. That motion of the water distorts your image of the penny. Just like the motion of the air in our atmosphere distorts our images of astronomical objects.
Ghez agreed to take on the quest, to search for signs of a black hole at the center of the Milky Way.
A decade ago, you couldn't look at the center of our galaxy with high resolution, so you couldn't distinguish stars from one another.
Ghez was able to correct the blurring effects of the atmosphere with a revolutionary new technology called adaptive optics.
So this little animation shows you the benefit of adaptive optics. You see the stars without adaptive optics, you turn the adaptive optics on, and all of a sudden you see stars. And in particular, you see stars near the center of the galaxy. Without adaptive optics, you would only see one big blob. And those stars are in fact the most important for us to track. We track all of them, but these are the ones that are the key to the problem. I mean, it doesn't hurt to take more.
Thanks to the new technology, the team could peer into the heart of the Milky Way with amazing precision.
Our view to the center of the galaxy is absolutely superb, and our ability to position stars at the center of the galaxy is like somebody in Los Angeles seeing somebody in New York be able to move their finger like this, okay, just 2 centimeters. That's the precision with which we can measure something that is 26,000 light years away from us.
Once the view was clear, Ghez could start the hunt. If there were a black hole at the center of the galaxy, its paw print would be found in the rapid orbits of nearby stars.
Keep our fingers crossed.
The conclusive experiment to be done that really demonstrated that it was a black hole is to follow the orbits of individual stars in the galactic center very, very accurately and with the highest precision possible.
When an object like a star approaches another, more massive object, the pull of gravity will make the star speed up. If it's orbiting close to a massive black hole, the star should accelerate to enormous speed and then whip around the black hole like a slingshot.
Okay, so we have the black hole here. The more massive it is, the more pull there is. The more pull there is, as it gets close to the black hole, the faster it goes. And we are measuring the speed of these stars. That's the key to getting the masses, measuring the speed of those stars.
This is our road map, and that's the center of our galaxy. There's a large cluster of stars that are orbiting the center of our galaxy, and by measuring the motion of stars, and in particular their orbits, we can figure out whether or not there's a central black hole. That environment in there, it's a crowded party.
Gez set out to monitor the partygoers, to track every movement of the central stars.
Basically, the way this experiment works is you take an image, you see where all the stars are, and then you come back sometime later and you take another image, and you look to see if they've moved. And so the second time we took an image, we knew we were golden. Those stars had clearly moved. This one moved to here, this one moved to here, this one moved to here, and so on.
As Gez continued to track the stars, she found some making dramatic hairpin turns.
It made a huge jump to over here. So it went whoop, all the way around. And it's moving on order 10 million miles per hour, so it's just speeding away.
Other astronomers clocked the stars with similar results. Not only were the stars accelerating to phenomenal speeds, their orbits were perfectly smooth. Gez knew that they had to be circling a single massive object. Most black holes are thought to be about 10 times more massive than our Sun, but the object at the center of the Milky Way was roughly 3 million times as massive. For Gez and Becklin, that could mean only one thing.
All other physical explanations of what was at the very center were gone. The only thing left was a black hole.
Not only was this black hole supermassive, it was millions of miles wide. Astronomers around the world admitted the evidence was impressive.
I have to say, when I first saw Andrea's video, I was stunned when I saw that star come out of the left side of the frame and go zipping around and go shooting off into the other end of the frame, and it moved around a point in space and nothing was there.
That we could, with our instruments, effectively travel to the center of the galaxy 26,000 light years away and collect the evidence for such an incredible object was really an amazing achievement.
It seemed undeniable, a giant black hole, and at the center of our Milky Way. But how could such a monstrosity come to be? One idea is that black holes are born out of the death throes of enormous stars. Like a red supergiant, a star 10 times more massive than our own Sun. Deep inside, temperatures soar above 1 billion degrees. Helium and carbon fuse into heavier elements: oxygen, silicon, sulfur. Eventually, the nuclear reaction creates iron, and the core stops burning. Then, the star implodes under its own immense gravity and goes supernova. What's left is a heavy core of subatomic particles, a neutron star. Only about 10 miles across, but of incredible density.
In fact, it's so dense that a teaspoonful of neutron star matter would weigh about 1 billion tons.
If the neutron star is heavy enough, 3 times more massive than our Sun or more, the implosion will continue.
Eventually, the gravitational pressure will be so large that the neutrons themselves will be crushed, and there'll be nothing left to stop the collapse.
Many researchers believe that the Milky Way is littered with small black holes, the dark, dense remains of dead stars.
There must be millions and millions of black holes zipping around our galaxy as we speak. But we don't see them in general because they're dead. They're corpses, and there's nothing there to light them up.
They might be invisible, but to a visitor, these small black holes, maybe 10 miles in diameter, would be especially deadly.
One of the scenarios that always gets me thinking is death by black hole.
Approaching a black hole, the gravity is so strong and space is so warped, it distorts the light all around it. If it's a small black hole, then soon you'll be distorted too, by tremendous tidal forces of gravity.
The tidal force is the difference between the gravity at your head and your feet. The gravity at your feet, if they're closer to the black hole, is a little bit stronger than the gravity at your head, and you feel that as something that is tearing you apart.
Stretching you from head to toe. The tidal forces unrelentingly getting stronger as they exceed the molecular forces that bind your flesh, as you snap into two pieces, and those two pieces snap into another two pieces.
And ultimately, you will pull your atoms apart. You will be, as we say, spaghettified.
And so you end up moving through space-time like toothpaste through a tube. And if I pick a way to go, that's how I'd want to go. It's got to be better than just getting buried. I mean, come on now.
A supermassive black hole, 1 million times wider, might at first seem more inviting. Since it has a larger event horizon, the pull of gravity is more spread out.
If you go to a supermassive black hole, the tidal forces are weak enough that you can fall not only through the event horizon, but deep down into the interior of the black hole.
So, with a good spaceship, you might be able to cross the event horizon into the black hole itself. Now, thanks to a computer simulation based on Einstein's own equations, we can see exactly what such a trip would look like. The supermassive black hole is surrounded by swirling light beams as superheated gas rushes into orbit at high speed. Light and matter are suspended by centrifugal force and then inevitably fall victim to the relentless pull of gravity. At last you cross the event horizon, the point where nothing can escape.
So let's imagine that we fall through the event horizon. That's the place where space is moving faster than light. We fall deeper down inside the black hole.
But don't expect the black hole to be black. Deep within, there's an inner horizon, a logjam of trapped light and energy.
At a certain moment, as we hit the inner horizon, there's this infinitely bright, blinding flash. And that's all the stuff that's been waiting there, trying to get out, is just held there at the inner horizon.
Unfortunately, you wouldn't have long to enjoy the view.
It would vaporize you. Roast you, vaporize you, marmalize you. Almost certainly, if you fell into a real black hole, you would simply, unfortunately, die.
Science fiction displays a bit more optimism, like the 1979 movie, The Black Hole. Space travelers do indeed fear this massive object.
I will travel where no man has dared to go.
Into the black hole?
Why, that's crazy.
Cuckoo is a Swiss clock.
But even more cuckoo, the heroes actually survive their descent into the beast,
Black hole is pulling us in.
where they're treated to a heavenly experience. Popular culture has cast black holes as the freaks of the universe. And the supermassive black hole at the center of our Milky Way, weighing in at 3 million times the mass of the Sun, seems especially monstrous. But is it unique? To find out, astronomers are probing distant galaxies to see if our giant black hole is one of a kind, or nothing special. The Sloan Digital Sky Survey is taking a census of the big galaxies within 1 billion light-years. For every patch of sky, a steel plate is created. Each hole represents an entire galaxy within our view. Fiber optic sensors are plugged in. Each measures the distinctive spectrum of light emanating from a galaxy's core and can detect signs of hot gas swirling into a black hole. You can see the results. Circled in red, virtually every major galaxy bears the signature of a supermassive black hole.
That was pretty amazing. Before that, we thought, yeah, maybe a large number of galaxies have black holes in them, but every galaxy has a black hole? That was something very interesting.
The closer we look to the centers of galaxies, the more we find these black holes, and the inventory is rising high. So any idea for the formation of a galaxy will now have to include some explanation for how you get a black hole in its center.
So how did every big galaxy in the universe end up with a giant black hole in the middle? To understand, we have to go back to the very beginning. The Big Bang.
You got the Big Bang handing you your birth ingredients, your hydrogen, your helium, your traces of some other elements. So it's kind of like this soup. You put it together and stir it.
The main stirrer for the soup is gravity, drawing together wisps of hot primordial gases. Over time, the clouds of hydrogen gas cool down and grow more and more dense, until some coalesce into the first stars. These are giants, hundreds of times bigger than our sun. They burn out quickly and dramatically in the flash of a supernova. What's left at the core is a black hole.
Perhaps the black hole becomes the seed from which the galaxy sprouts. The gravitational seed that is used as an attractive force to accumulate the rest of what we would today then call the greater galaxy.
Possibly seeded by black holes, the infant galaxies dance and orbit one another as gravity pulls them closer. So our Milky Way galaxy, as this time-lapse simulation shows, was not born in one single event. Instead, it was built over billions of years from a swarm of smaller galaxies smashing together, merging.
But if another galaxy comes too close, they will each feel each other's gravity. And in that collision, what started out as a stately ballet of stellar orbits moving around the center of their galaxy has now become this maelstrom. There's no other way to say it. Galactic cannibalism, that's what they're doing. They're dining on their neighbors, eating entire galaxies. Well, for every galaxy you eat, if that galaxy has a black hole in its center, it's going to eat the black hole. The black hole will work its way down to the center of the large galaxy, making the center of the galaxy bigger as well as the galaxy itself. It's just that simple. The big galaxies get bigger, and the little ones get eaten.
Galactic cannibalism is how galaxies grow, and with them, the black holes at their centers merge and grow bigger. But what does the presence of such a monster mean for the life of a galaxy? Brian McNamara believes he's found the answer, and it isn't pretty.
That's it right there. We got it. That's it. Okay, so you want to go...
McNamara studies the life cycles of the universe's biggest structures, galaxy clusters.
There it is. That's the galaxy. So that's what we've been looking for. This is the giant central galaxy in a galaxy cluster. And each one of these little dots here on the screen is a giant galaxy as big as our Milky Way, maybe even a little bit bigger. And they're all bound together by their own mutual gravity. So they're all buzzing around this giant galaxy like bees buzzing around a hive.
McNamara probes his galaxies with multiple tools. Optical telescopes, radio receivers, even X-rays.
Ah, there we go. Check that out.
X-ray images reveal a vast cloud of hot gas through the whole cluster, across hundreds of thousands of light years.
There's an atmosphere of gas that pervades the entire galaxy cluster. And it's an atmosphere like our atmosphere, except that it's far less dense and it's much, much hotter.
But when McNamara looked at X-rays of the gas around certain clusters, he saw that vast clumps of it appeared to be missing.
I was blown away. I'll never forget the moment we got the observations, and lo and behold, these two giant cavities showed up in the X-ray emission.
The size of the cavities was astounding.
That's 200,000, 600,000 light years from end to end. So between that cavity here and this cavity here, we could stuff 600 Milky Ways in there. It's just astonishing. The energy involved is huge.
Something powerful had pushed the gas away, across vast regions of the universe. McNamara traced the power source to the center of a giant galaxy, a supermassive black hole.
So we could see the beam coming out of the black hole and ending up in these big cavities.
But how can a black hole, a creature famous for devouring everything within its grasp, spew energy across the universe? The answer lies in the way matter falls toward the black hole. It turns out, nothing goes straight in.
As matter falls in, what we know now is that it spirals around in a disk, okay, very much the way when water goes down the drain. It doesn't just go straight down the drain.
Just as water spirals down a drain in a whirlpool, matter and light spiral at high speed into a black hole.
And the speeds that matter can achieve around that black hole approach the speed of light. And when matter travels at that speed, it gets a tremendous amount of energy.
Matter falling into a black hole is a lot of stuff trying to get into a very small place. And so it's like trying to fill a dog dish with a fire hose. Most isn't going to get in.
The black hole chokes on the influx. And the high-speed whirlpool of matter produces a powerful magnetic field, coiling around the black hole and shooting the energy outward. These enormous jets of energy, hundreds of millions of times the power of the sun, can blast right out of the galaxy.
There's no question that the black holes at the centers of galaxies have a profound influence on their surrounding. They send out these huge jets moving at almost the speed of light. And those jets can send shock waves into the surrounding medium and change their surroundings completely. They have a dramatic influence.
Not only can they blast away huge quantities of gas, but they may even sterilize the galaxy so new stars can't form.
The supermassive black holes at the center may be responsible for limiting the size of galaxies. In principle, galaxies can grow to very, very large sizes, and what we see in the universe is that they don't. And we think that the supermassive black holes at the center may be the culprit. They may be responsible for preventing runaway growth of galaxies.
We usually think of black holes as God's dumpster, but they really are actors on the galactic stage.
If supermassive black holes can wreak so much havoc, what's to stop our own monster of the Milky Way from wiping us all out? It all depends on the monster's diet.
Most of the time, a black hole isn't eating. It fasts more than it feasts. But when a black hole feasts, it can have a tremendous effect on the surrounding galaxy.
The more black holes chow down, the more matter and energy will blast outwards.
One of the key differences between galaxies with supermassive black holes is whether or not their black holes are lit up, because they're basically binging on a lot of material in its surroundings.
For years, our black hole seemed to be fasting, and the Milky Way was peaceful. But in 1999, the Chandra Space Telescope detected a powerful signal from the galactic center.
Station 34, Chandra OC.
An explosion near the event horizon.
Playback. I'll give you a call
Is this the beginning of a black hole binge? For trackers of the galactic center, the blast is a wake-up call.
There was a hot piece of news. A remarkable fact for all of us was, for many years, how inactive the black hole was. And all of a sudden we saw, well, there's an object there which wasn't there before.
Reinhard Genzel has been watching the galactic center for nearly 2 decades. Like Andrea Ghez, he's been tracking the orbits of stars, helping to prove the existence of a black hole at the heart of the Milky Way. Now both Genzel and Ghez will shift their focus and try to measure the black hole's appetite.
One of the big mysteries about the black hole at the center of the galaxy is when we see emission matter falling onto the black hole, or rather the black hole eating up its surroundings.
Genzel and Ghez are joining a worldwide effort. Chandra in orbit will take X-ray pictures of the galactic center. At the same time, 5 major observatories on the ground will probe the black hole, all trying to count calories. Genzel heads south to Chile, while Ghez and Becklin climb a mountaintop in Hawaii. Telescope time is precious. There's no room for mistakes.
When you're there, it's an incredible rush. I mean, you're very much on for the few nights that you're there, hoping the weather cooperates, hoping that the instrument cooperates.
How's the Yak 4 look on the oscilloscope? Does the timing look okay?
Better now.
Okay, let's see if there's something there. Madeline, we're ready to go?
The teams have 5 short nights to find out how much the black hole is eating by measuring the energy that flares out.
Zoom in a little bit more. All right, so first night. Doesn't look like we've got any flares.
Chandra headquarters in Cambridge, Massachusetts. The first night turns up only noise.
4 more chances, guys.
Night 2, Chile has problems.
No, we have to redo the acquisition of it.
Even if there are flares, the Chilean telescope can't see them.
The correction was
unstable.
Yeah, unstable.
A patch of humidity is confusing the computers. The crucial adaptive optics aren't working, and everything's a blur.
Extremely.
Okay, now we have a problem with the 8 meter, with the main mirror. The 8 meter mirror seems to be deformed.
In Hawaii, it's not much better for Ghez and her team. The Galactic Center is playing hide-and-seek behind overcast skies.
We're fighting with clouds. It looked better just a moment ago, so it looked like we were just ready to go, but now it's looking like yuck.
The Hawaiian forecast predicts even more clouds tomorrow. The team is getting anxious. Finally, on night 3, the German team's luck changes.
Very in correction.
Look at this. You're right. It's really flaring. To calibrate.
In Chile, they spot an outburst.
That's the best flare event that we saw during this run. Definitely.
A new point of light appears in the starfield, one that wasn't there before.
Very nice, very nice.
Here we can clearly see a region between those 2 sources where there is no other object. And here we have the same region, the same 2 sources, and now in between we see an additional source. So this is the flaring state of Sagittarius A star.
JPL-COM, Chandra OC.
When the Chandra team downloads their data from space, they see it too.
Oh, yeah.
The X-rays show a spike that coincides with the Germans' flash of light. Genzel checks in with the Hawaiian team, but they're in the wrong time zone.
News from our colleagues, of course, telling us that they are a few hours further west, so the sun hasn't even set yet.
The Galactic Center hasn't risen above the Hawaiian horizon, and Ghez has missed the flare.
This part kills me. Waiting.
But the next night, Ghez finally gets what he's looking for.
Well, that image a whole lot better.
Really? Yeah. Really?
So in fact, we can see flaring activity where we think we're seeing matter fall into the black hole. And just a few minutes later, it was absolutely gone.
This now you see it, now you don't flash of light is an explosion of energy produced when matter rushes toward the black hole and some escapes.
We were taking measurements and you didn't see anything from the black hole. All you saw was a star, and then bam, it was there and bright. And 15 minutes later, it was gone. So that was our moment to make the measurement, and it was extremely exciting to know that we'd actually been able to catch it.
The teams are thrilled to capture a handful of flares at the heart of the Milky Way, but they're just snacks. Nothing compared to the giant jets seen in distant galaxies. What's more, they're looking like rare events. There's simply not enough matter near our black hole to provide a large continuing feast. It seems, at least for now, the giant's plate is empty.
Our black hole had a wild teenage life. I'm pretty sure of that. It had jets. It threw a lot of matter out. It had a grand old time. And now it's decayed into the old folks' home.
But what would it take for the monster of the Milky Way to come out of retirement? Could explosive jets of energy blast across our galaxy in the future? Tantalizing clues are turning up in the coldest place on Earth. A Smithsonian team is tuning into high-frequency radio signals from the Galactic Center. The best reception is at the South Pole. Not as nice as Hawaii, but the date is worth it.
There's some of the gas falling in toward the black hole in the galactic center.
Reading the radio signal, Anthony Stark detects just small amounts of gas feeding the black hole. Nothing too serious, but farther out, about 400 light years from the galactic center, he can see signs of something much more alarming. A vast ring of matter is gradually growing bigger.
This storage ring then builds up until it coagulates into a single gigantic cloud of about 30 million solar masses.
When the ring reaches a tipping point, it will condense into a giant cloud, triggering a dramatic starburst event, a storm of stars forming and dying quickly. What's left of the gas cloud will spiral down into the grasp of the black hole,
which then rapidly spirals in and feeds the black hole in the galactic center, making the Milky Way an active galaxy.
When the feasting starts, the fireworks will be seen across the Milky Way. But don't bother marking your calendar. Dinner time isn't scheduled for at least 10 million years. The Milky Way will survive its black hole's upcoming feast, but it isn't likely to survive the threat further down the road: galactic cannibalism.
Our galaxy, the Milky Way, is not immune from these colliding galaxy scenarios. We've got neighbors.
2 million light years away, our closest neighbor, the Andromeda Galaxy, is charging toward us at almost 700,000 miles per hour.
We're falling towards each other, and one day we will collide.
Knowing the galaxy's dimensions and the laws of gravity,
what our simulations show is what could happen basically in quite a few billion years from now, when the two galaxies will actually approach each other and merge.
the merger will take more than 2 billion years, while the galaxies circle and entwine.
Imagine what that might look like from another galaxy. They'll see two grand, beautiful spiral galaxies moving towards each other, slowly losing their shape. They'll see new avenues where stars and gas can funnel down towards this newly formed center, feeding this reborn monster.
The collision will send a blizzard of stars and gas in all directions. Some will shoot toward the crowded core of the new galaxy, spurring massive explosions.
In the process of merging, there will be a very strong starburst event occurring at the time of the merger as all of the gas is being funneled towards the center.
Amid the turmoil, chances are our little solar system will either witness a spectacular show or be flung out of the galaxy into the voids of space. the Milky Way will be destroyed. But what about the black hole at its center? Most likely, it will merge with Andromeda's, a monster 50 times larger. Stars and galaxies may come and go, but supermassive black holes just get bigger. Once considered freaks of the cosmos, black holes are coming into their own, claiming their place center stage in a violent, changing universe.
As we forge ahead in trying to understand how we came into being and how all of the matter got put down in the universe, we can't leave black holes out of the picture because it seems they play a fundamental role on very, very large scales.
Black holes not only wreak havoc upon the landscape in which they're embedded, they actively shape the landscape. So black holes are kind of the spice of the universe.
Black holes are a major player in the evolution of the things that light up our night sky. They are, in a sense, the secret shadows behind the walls of the galaxy.
Patrolling space like a sentry, the satellite telescope SWIFT is on constant lookout for cosmic disasters. And when it finds one, down on Earth, word spreads quickly. Every few days, the satellite spots a violent eruption in deep space, sending dozens of stargazers scrambling. Whether they're seasoned pros or high school amateurs, their goal is the same.
Go to camera focus mode, and then we're gonna need to move the dome. Casey?
To catch a glimpse of a star in its final death throes, going supernova. And leaving in its wake the strangest phenomenon in the cosmos, a black hole.
Nothing survives encounters with black holes. The black hole wins. It wins every time.
When something falls into a black hole, it's essentially gone from our universe.
They rip stuff apart and eat them. And then they burp and they're ready for the next course.
And now, evidence of something even more ominous. A new kind of black hole, of unfathomable size and power.
That's a big galaxy, and right down at the center, we think there's probably a black hole that's got a mass that approaches 1 billion suns.
Today, scientists are finding black holes are bigger, stronger, and more destructive than they ever imagined.
It creates energy fields that would fry any life in its vicinity.
Not only do they consume everything that comes near,
You stick your finger down in there, you ain't getting it back.
but their power may reach across galaxies and beyond.
Did the universe really have to be made with these things in it?
We'd like to think they're far, far away. But what if, in our own cosmic backyard?